So that would have been probably for a short period of time the grandest waterfall on Earth. If you figure a waterfall 4 to 5 miles wide and 900 feet high, and the estimated flow through there was about 300 million cubic feet per second, which is, if you took every river on Earth, every river from every continent, added it all together times 10, you would have roughly the flow coming through Grand Coulee. And then what happens is lower Grand Coulee, you see that the monocline, the flexure of the monocline weakened the rock along the ridge here. And so the water began to exploit that weakened bedrock, basalt bedrock there. And so the lower Grand Coulee becomes confined. It almost follows parallel the monocline and then spills out right here into the upper rim of Quincy Basin. And here's what's called the Great Notch at the head of Grand Coulee right here. And what's interesting is the bedrock elevation, all from up here at the top of the notch, all the way across here is about 2,400 feet, like I pointed out earlier. And that's basically, once the water in Lake Columbia, which occupied now, what is now occupied by Franklin Roosevelt Lake, rose up to that level, it began to spill over the northern rim of the basalt plateau. But also to begin cutting the upper Grand Coulee, which came right down here. Now, I'm going to call your attention to this feature right here, which is called Steamboat Rock. And you know, when you begin to look at these flood type features, you'll see that a lot of them have names that are suggestive of their connection with hydrology and water flows and stuff. You know, Steamboat Rock is actually used several times, but this is probably the most well-known Steamboat Rock that sits right in the Coulee, and it's a remnant. If the floodwaters had persisted for a matter of a few more days or a few more weeks, there would be no Steamboat Rock. It's very much could be compared to Goat Island in above Niagara Falls. But let's go on here. Here's an aerial view that was in Paul Weiss's little book from the 70s. And we're looking south down upper Grand Coulee, and there's Steamboat Rock right out there. And you can see it's very mesa-like. It's very, compared to some of the mesas in the Southwest, it's remarkably similar in scale and size. Again, like I said, it's a remnant. And prior to the flood, you have to bear in mind that all of this across here, this was all continuous. Here, there's 1 to 24,000 of Steamboat Rock. You'll notice that there's a tributary canyon coming in here, Northrop Canyon coming in, which was tributary to the Coulee. Steamboat Rock is right here. We see Castle Rock, and here's an unnamed cataract right there. So if anybody has any good names, maybe we could come up with something and get it on the maps, because nobody's bothered to name it yet. Now, I don't know, maybe. And here's an aerial photograph that I took of the unnamed cataract, and here's Castle Rock. Right there, that little corner is a section of Steamboat Rock. Now this is interesting because here's where you see granitic rocks giving away. See, there's granites out here, and these granites give way to the basalt. And this is right there at that transition between these, the granite bedrock that actually extends up into British Columbia, and the basalt plateau actually occurs right here in this region. Here's an old photograph, aerial photograph of Steamboat Rock. Here's one from the ground, and this is showing that there's actually a coulee on the top of Steamboat Rock. Now, based on the trim lines that are on the hillsides outside of Grand Coulee itself, they were able to calculate that the minimum depth of water at one point over the top of Steamboat Rock was 200 feet. And so this right here, this spillway right here would have been carved. So again, most likely what you first had was a sheet flow moving over the basalt. It exploited weaknesses in the rock and then began down cutting. Once it began down cutting, the water then became confined to that channel. And this is the gravel quarry that's at the mouth of that Northrop Canyon, which is a very interesting thing, and I really like to get deeper into the sedimentology of this whole thing, because there's a whole story written here. But we don't have a lot of time, but we can see that some of the clasts within these sediments are pretty sizable. But we also see some interesting bedding going on right here. which suggests you had flows coming into Northrop Canyon, into Grand Coulee. You also had backflows going out of Grand Coulee back up into Northrop Canyon. Now Northrop Canyon is inhabited mostly by rattlesnakes. And here is a Google Earth of the Great Cataract Complex that separates Upper Grand Coulee from Lower Grand Coulee. And this is really one of the most fascinating. Here again, it's from Shelton's book. This is only part of the complex, and you can see here one great alcove, and then you see part of a separating rock here that are called blade rocks that separate one alcove from another. And notice the bedrock. This is something that we see very typically, this scoured bedrock. Now, the water flowing over this bedrock is estimated to have been right here in this between 350 and 400 feet deep. This is what's called a receding cataract. So as the water is rushing over the lip of this thing, it's plucking the basalt and eating it upstream. And down below Dry Falls Cataract here, you can see these gigantic boulders, some of them which are at least the size of the room that we're in right now, piled up. And just for some scale again, here's Niagara Falls. Who's been to Niagara Falls here? Okay, so it's pretty impressive, isn't it? I think it's about 125 feet in height. Somewhere on this classic horseshoe-shaped profile. Here's another version. Now what I've done is I've taken this photograph and I've superimposed it at the same scale over Dry Falls, so you can kind of get a sense of the magnitude of this thing. And we're actually only looking at part of the complex. You can actually see there's more of it. It continues. The whole complex is roughly 5 miles wide, a little bit shy of 400 feet in height. So you can see that it would have utterly dwarfed Niagara Falls. And here's from the ground level, looking at the two westernmost alcoves. And again, I've put Horseshoe Falls of Niagara in there at scale. So you can really begin to appreciate Now, the thing is that at the peak of the flood, you wouldn't have seen really a waterfall here. What you would have seen was a bump in the water. You would have seen just very turbid water flowing, choked with a lot of icebergs. And I'll show you how we know that there were a lot of icebergs in the water. Only at the latter stages was this actually a waterfall. As the source of the floodwaters began to decline, and we went from 300 million down to 200, 100 million, and eventually the flow ended. But during only the latter stages would we have actually seen a waterfall here. And this is below Dry Falls, looking down into the head of Lower Grand Coulee. And here where you can actually see, when you look at the east side compared to the west side of the Coulee, is the elevation difference in the monocline really is apparent. And these are the kind of things you see. This is the Grand Ronde basalt, which was one of the big basalt outflows back in Miocene times. And what the floodwaters did was basically stripped the overlying basalt layer by layer and left this shelf. So this is an erosional shelf rather than a depositional shelf. You can see that the truncated sides of the Coulee are here, and they left a lot of hanging valleys, which are generally dry except during rainfalls, which they then have temporary waterfalls. Notice along the flanks, this is not normal talus. This is basically flood sediment. This is bouldery material that was being carried in the water of the flood that was deposited along the flanks of the Coulee, also along the floor of the Coulee once the floodwaters subsided. And here is at the mouth of the Coulee looking north, so you can really see those hanging valleys. Whoops, I don't want to fall off the stage here in my excitement. But we're standing on the northern edge of the Ephrata Erratix fan looking into the Coulee mouth. And here's the topo map showing Lower Grand Coulee spreading out into the fan here. Moses Lake is actually into the fan. We can look at the fan and there's a down current fining. We have very coarse, large boulders up in the northern end, and then it gets progressively finer as we move to the south and as the water stills into the Quincy Basin. And that's roughly the outline of the fan itself, the fan, which is the material that was eroded out of the coulees and then deposited, because when the water is confined, it has a high energy, right? It's moving faster. When it opens into a basin, it slows down. As it slows down, its competency to transport sediment declines, and it begins to deposit stuff. And it deposits the largest material first, and then successively finer material. And this is another paleocurrent indicator that you can use when you're looking at a section of stratigraphy like this. If you see very definite larger clasts or boulders on one side getting progressively smaller, you know that that's the current direction. So here's another digital relief map of Quincy Basin, and you can see the Frenchman Hills anticline right here that served as a major flow obstruction to all of this water. Now, a couple of things I'm going to point out to you here. Here's the Drumheller Channels, and this was the parting of the waters I was talking about. Drumheller Channels, this right here is 9 miles wide, okay? So what happens is Quincy Basin levels out. So you've got up there where the Grand Coulee is, you've got it's about a 20-foot fall per mile, right? And then it almost levels out right here in Quincy Basin. So what happens is that the water slows down and it pools up here in Quincy Basin. But there were 3 great spillways out of the western rim over here of the basin. You had one here, and one up here called Crater Coulee, which we're going to look at a little closer. Crater Coulee, the Babcock Ridge, which is this ridge right here, is 400 feet above this. So in order for the water to spill over Babcock Ridge here and cut this coulee right here, it had to be 400 feet deep. And that's a lot of water, and bear in mind that the spillway out of Quincy Basin is 9 miles wide. So you would have had basically a temporary river here 9 miles wide and somewhere between 300 and 400 feet deep. And as it's hitting the Drumheller Channels, what's happening is the gradient is going from almost level to, again, about 15 feet per mile. So what's happening is once that water hits that rim, it starts speeding up. And then, of course, you can see what's happening here is that it's beginning to create that erosional forms, which is typical scabland-like. Here's the fan itself. Now, this fan is a couple hundred feet thick, and it covers hundreds of square miles. And you can see a mixture of mostly basalt, but there's also some pink granites in there that probably had their source either north of here, where I pointed out to you that there was granite bedrock outcropping north of the basalt plateau on up into Canada. And you can see some of that pink granite right there. But this is, of course, the typical basalt of the Columbian basalt group here. And you can just see it's spread over many, many square miles.
Could the granite have just been caught up in the glacier?
Yes, I'm guessing it was probably in the glacier, or it may have been transported. See, one of the things we won't get into today, but I've done two traverses up the Okanagan Valley, and I'm almost convinced now that you had enormous floods heading down the Okanagan Valley. And there are this pink granite up in that area, so I'm guessing that might have been one possible source. But it's going to take another couple of trips back there, I think. And so I will mention that if anybody's interested, sometime this summer, I'd like to get back out there for about 8 days and fill in some of the gaps. And be great to have a team. So you can get a sense here of what the Ephrata or radix fan actually is. And this is from the air, about 2,500 feet altitude. The larger rocks here, like that you see right here, that rock there is about the size of the room we're sitting in. So it gives you a sense of the scale. And here's, by comparison, Mars. Now, I'm not planning any expeditions to Mars next summer.
Man.
Pardon?
I said man.
Oh, sorry. It's on the bucket list, though. Okay, now we're going to move over to Mighty Moses Coulee, which is this feature here, which is very close to Grand Coulee in scale and grandeur, which again, to me, is a little bit problematic within the standard explanations. What we got here, Withrow moraine, here very clearly demarked. You'll see that the head of the coulee is actually would have been up under the terminus of the Okanagan lobe, which I find interesting. But it comes down, there's an upper Moses Coulee, there's a right angle turn right here called the Devil's something. A lot of stuff having to do with the devil out here, I've noticed. The devil this and the devil that. Okay, and then here's lower Moses Coulee, and it meets the Columbia down here in this V-shaped form. Yeah, here you can see, here's lower Grand Coulee. Here's Moses Coulee extending right off the southern terminus of the Okanagan lobe. One of the things I'm having a problem with is how to explain Moses Coulee as a result of the draining of Lake Missoula. And here you can see the Withrow Moraine, you can see the head of, you have Green Lake and Jameson Lake occupying, which are basically, a lot of these lakes occupy scour troughs that have been scoured out and left behind as part of the erosion. Elevation 570 miles. And again, you'll see that there seems to be no genetic link between the head of Moses Coulee and any flow that would have been coming from the west.
Water on top of the ice.
Superglacial. Now see this, I'm looking and considering possible superglacial and subglacial.
Yes.
Yeah. As being something that needs to be explored further. And this would have just a little graphic to show, but there's something else that I find very interesting. You won't see this clearly in this unless I point it out to you. Up here, this is called Alto Lake, right here. That's right, and we're going to be coming back to that in a minute. Because there's a coulee that follows the western margin of the Okanagan lobe, which I find very difficult to explain by waters issuing from western Montana. But here is the transition between Three Devils Cataract Complex, that's what this is called. Not just one devil, but three devils, right in here. See, and this is the transition from upper Moses Coulee to lower Moses Coulee is right in here. And there's a whole set of cataracts and stuff that's in here. And then you get down here and here's lower Moses Coulee. There's moraine in the coulee itself, which is interesting, and I imagine we're going to be running out of time soon because I'd really like to get into some of the background on some of these thinking, but the assumption has always been that radiocarbon dating of organic material found associated with the Okanagan moraine is dated to up to 20,000 years, right? So the assumption is that the moraine was formed by the Okanagan lobe, which I assume to be correct, but that Moses Coulee had to precede because the moraine is deposited down in the coulee itself. So the coulee would have had to already have been there, right? Which would have made Moses Coulee more than 20,000 years old, which would have made it thousands of years older than the Scabland tracts and even Grand Coulee. I question that, and the reason is because if Moses Coulee was produced by a subglacial flood, we know from studying Jökulárlóps up in Iceland that after the hydraulic pressure is diminished when the floodwaters recede, that the ice roof will then collapse down onto the substrate. And I would suggest that might be an explanation here. Because if we assume that Moses Coulee was thousands of years older than the supposed draining of glacial Lake Missoula, then to what do we attribute it? Because Moses Coulee is really phenomenal, as you're going to see here. We'll get into it. Here is the confluence of the Moses Coulee with the Columbia. And you can begin to see there's just like where the Palouse hits the Snake, there's massive gravel bars splayed out at the mouth. And we had massively augmented flows coming down the Columbia, and we had the flows coming down Moses Coulee there. Here's an aerial shot looking down onto that confluence. So we're looking up Moses Coulee right here. And here's the Columbia. The next one can actually see, here's the Columbia River down here. And you can see the scale. This whole gravel deposit, I think from northern end to southern end is close to 10 miles. It's at least 400 feet thick. So this is material that was quarried out in the creation of Moses Coulee. And if we go back one, you're going to see that, yeah, here we go. Here's looking at the eastern flank, looking south. And you can see here how the pre-flood drainage divide was basically irrelevant to this flow that created Moses Coulee. The wash through here and basically truncated these hills. You can see typical scabland formation along here. There's about a minimum of 200 feet of coarse gravel, cobble, sediment forming the floor of the coulee in here. And here you can see the extensive gravel that came out here. The modern day Columbia dissects that gravel. And here we have something very interesting. This is called West Bar. And I pointed out to you Crater Coulee a few minutes ago. Here, this is it right here. This was one of the spillover channels out of Quincy Basin. And this rim here is again 400 feet above the sill of Drumheller Channels. Let's take a closer look at this. First, we'll look up into the mouth of Moses Coulee from standing on the gravel bar. Again, notice this wash up, this gravel, coarse gravel sediment that you find deposited all along the flanks. Just contextual here. Here's Quincy Basin, here's West Bar, here's one spillover channel, here's another one. Now you can see them pretty clear here. We've got Crater Coulee right there. We've got Potholes Cataract there and Frenchman Springs Cataract right here. So there was so much water coming into Quincy Basin that even a 9-mile wide, 400 or 300 foot deep flow over this spillway was not enough to carry the volume of water coming in at the north end. So it ponded in this whole thing and spilled over in these 3 places on the western rim. And here is Potholes Cataract, and it was a map of this that was newly released by the U.S. Geological Survey in 1910 that first piqued J. Harlan Brett's interest in this whole. He looked at this map that had been released of Potholes Cataract and said, what the heck is that? And this is what led to this 30 years of study, which is interesting. 1910, same year that Pardee wrote his first paper on glacial Lake Missoula, and of course the same year that Mark Twain died as Halley's Comet was coming over. Not that that has anything to do with any of it, but it was an interesting year. And here's Potholes Cataract from the air, and here's, we find the remnant blade rock that separates the 2 great alcoves. Down here in the distance is the Columbia. And actually, you can't tell too much from here, but when you see it firsthand, you realize that the top of this is all Scablands. So the water at one point was completely overtopping all of this. And here is standing on the rim of the south alcove. And this is part of the north alcove over here. The Columbia is actually way down in here. And here's Frenchman Springs Cataract, the southern spillway channel out of Quincy Basin. And there's a Google Earth where you can see the blade rock that separates the 2 alcoves. Had the flood continued at some indeterminate length of time, from days to a few weeks or whatever, that blade rock would have been gone. And here's looking into Frenchman Coulee, and you can kind of see the roads down there to get a sense of scale. And now we're going to look at West Bar, which is this, which you'll notice here that here's Quincy Basin, and here's Moses Coulee coming in, meeting the Columbia, and then you come down here, and here's this 3-mile long, 400-foot thick gravel bar. And there's an aerial shot of the gravel bar. And this is one of the most well-known of the giant current ripple formations. The largest of these current ripples have amplitude of 30 to 50 feet and a wavelength of 200 to 400 feet. So they're pretty impressive. I've got another shot that I took from across the river where you can see, and there's actually right, if you look very close right there. Now, if that guy had been standing there during the flood, he probably wouldn't have survived. And again, you see more of this wash-up gravel over here. And here's Drumheller Channels. And this is very interesting stuff up in here, this erosional forms. Yeah, so this was the parting of the waters. Here's Drumheller Channels, comes down. One flow hit Saddle Mountain anticline here, flowed off to the west. The rest of it came and spilled around this way. And this is that's this stuff here. I'm not sure what to call that. Anybody got any good suggestions?
Brandon, you're probably down about 5 minutes if you want to do any Q&A.
Oh, okay. Well, anybody got any quick questions? I sure would like to show 1 minute on some of these basalt bowl, some of the erratics. Yeah, what is it?
What was the source of all water?
Pardon me?
What was the source of all water?
Well, you know, you had nearly over 1 million cubic kilometers of Cordilleran ice, which is now not there. And you had probably 1/4 of that was in the headwaters of the Columbia, right? We did our second trip to Canada last summer because what I was trying to do was see those north-south transecting valleys like the Purcell Trench and the Rocky Mountain Trench as possible conduits for meltwater. And that will be a whole nother discussion then maybe I can come back in the fall or something and do a follow-up, and we can get into that.
What was the time frame from start to finish?
The time frame, it depends on how you date it. Now, the dating is based on a Mount St. Helens set S tephra that's sandwiched in some of the slackwater sediments near Wallula Gap. That ash is dating to about 12,900 to 13,000 years. The thinking goes like this. And we don't really have time to get into that, I guess, because we're only got 5 minutes left. But basically, in the slackwater sediments, you have what are called rhythmites, which are layers that were, whether they were produced by hydraulic pulsation within one standing body of water or were produced by separate floods, is one of the controversies. But you find this Mount St. Helens set S tephra sandwiched in there, which has been accurately dated to 13,000 years. Over that is about another 14 or 15 or 16 layers, right? If you assume that each of those layers represents a separate outburst flood from Lake Missoula, you then have to extrapolate from that and assume how long it would take to accumulate 400, 500 cubic miles of water in Lake Missoula, which is generally taken as 50 to 100 years. And then from there you can extrapolate based on the number of layers. If each one was a filling of Lake Missoula, it's going to take between 2,000 and 3,000 years for the entire phenomena. Yes?
It just seems like this idea of 70 or 80 different outbursts and all that you'd be able to tell the difference when you look at the erosional features between the effects of multiple outbursts. What you've been showing us sounds like the simplest explanation is a single event,
Well,
that's the line that you sounded like you've been following.
that's the hypothesis. But I'm looking at two events, bracketed, because if you look at not 70 or 80. I'm having trouble with that for the simple reason that I'm having trouble with getting my head around even one glacier dam holding in 2,000 feet of a hydraulic head of water. Because, looking at modern examples of outburst floods, what you see is that typically the largest outburst floods, which are caused by the eruption of Vatnajökull in Iceland, are 3 orders of magnitude smaller. I mean, the largest modern Jökulhlaups is less than 1,000th of the flow that came through Grand Coulee. Okay.
Build some more continental ice sheets to see the effects. So give it another 50 years and go look at Antarctica.
Well, maybe. Yeah.
What was the time frame from dam break to empty?
Well, probably a couple of weeks, because if you've got 520 cubic miles of water in the Missoula Reservoir, and you've got basically Pardee calculated 9.46 cubic miles per hour going through the Clark Fork Valley. So do the math, 9.46 into 500. But of course you're going to have diminishing current flow, so the initial outburst is going to be, the Q, your peak discharge, is going to be much greater, and it's going to diminish throughout there. But clearly you can, at 9 or 8, 9 cubic miles per hour, it's not going to take but a few days to drain the entire reservoir. Yeah.
Why did this happen further to the east? Why don't we see the same phenomenon?
Mainly because of the gradient. You see, from the discharge points at the head of at the Columbia Basalt Plateau to the ocean, you've got a much steeper gradient. But there are mega flood features all up and down the Mississippi Valley, up and down the Missouri Valley, the St. Croix. I mean, yes, you can go across the entire. I've actually traveled with Brad over there through most of the southern margin of the Laurentide ice sheet, and there were catastrophic floods everywhere. But they didn't do the same amount of work as we saw here, simply because the gradients, to get from the southern margin of the Laurentide ice sheet there, say in the headwaters of the Mississippi down to the Gulf of Mexico, you're looking at 3 times the horizontal distance as you're looking at from the southern margin of the Cordilleran to get to the Pacific. That's the main difference. Another one of the most dramatic examples of how we're looking at major catastrophic flows are the erratics that are found strewn by the thousands throughout the flood path. And if you look here, you'll see up here on the ridge, you see these giant erratics up here. There was actually 2 people standing here, and I took them out of the picture just so you could get a sense of the scale of the thing. Now I'll put them back in. Now, again, there are thousands of these things. And here's another one. stranded on a ridge 400 feet above the modern Lake Chelan that you see right down there in the background, right there. There's a hell of an erratic. 400 feet above the Columbia, just by Wenatchee, Washington. So how did those erratics get there? This is one of the most famous ones, Yeager Rock. What's interesting about this, you see it's sitting in a berg mound. So when you've got icebergs being carried in the floodwaters, those icebergs are not clean ice. They're very dirty ice. They're sediment laden. So when an iceberg comes to ground, it melts away, it'll leave what they call a berg mound, right? And so you see that this Yeager Rock is sitting right there in a berg mound. And this is an interesting graphic from an 1866 book on geology, illustrated by Edouard Rieu, who was the illustrator for all of Jules Verne's original novels. But based upon Louis Figure's description, he depicted, this is what Figure was theorizing back in 1866. And when I saw this, I said, well, this is exactly what, depicts what we're seeing there throughout the Scablands channels and sort of the scale of the thing. Icebergs being carried into torrential floodwaters, erratic boulders on the ice sheets, which is a thing that demands explanation in itself. And the last thing I'll show you, and I pointed out to you earlier, Alto Lake, which is right here. Well, if you look at this right here, here is a coulee. And this coulee marks the western edge of the Okanagan lobe, right? And if we look at that coulee, here's a Google Earth. Why is it so washed out? Did we turn the lights back on? Oh, that's to tell us we have to leave? Yes. Can anybody can pay off the guard for an extra? There we see Alto Coulee, and Alto Coulee marks the western edge of the Okanagan lobe. And if we go through it, here's from the ground, here's looking south through the coulee, here's looking north, and what I did was a transect through it, showing its relationship to the Okanagan lobe. The coulee itself, it was one of the margins of the coulee, so it's an ice marginal channel. And if it was flowing rim full, I've put the Empire State Building in there just for scale. Now, my point there of Alto Coulee is that when you look at this, there's Alto Lake right up there. So again, I'm having problems going, okay, now how exactly do we get the water from western Montana over to Alto Coulee with the Okanagan lobe intervening? And why would it not deflect south either through Cheney Palouse or Telford or Grand Coulee? Why would it go over there and form that ice marginal channel? Well, I think you can actually trace the source of Alto Coulee right up into the Okanagan Valley in British Columbia. And that's one of the things that I'm interested in following up on. So we won't get into the ice dam here, other than this will be, I promise, the very last thing. I did 2 transects. One right here where the valley is constricted, and one right here where the valley opens out. Now right in here somewhere is where the ice dam water interface supposedly occurred, right? So first we'll look at this transect, cross section, and then we'll look at this one right here where it widens out into the basin. So here's a northeast to southwest transect. The high water mark was at 4,200 feet. So I put that in right there, right? Now I'll put the Empire State Building in for scale. In the next one, I've gone into the basin, put the high water mark at 4,200, and now I'm going to put the skyline of Atlanta in there for scale. So you can really begin to get a sense of how enormous these flows were. Here's a map of Atlanta, and the green dot is us, right there at Fernbank Museum. If that flow was flowing to our west from here, and we were right on the edge of it, it would be basically that wide. So all of downtown Atlanta, bye-bye. And everything from here for 7 miles over. And then I did one more with the skyline of Atlanta, and I put that 2,100 foot water flow through Clark Fork in there. And see, here's why I'm having trouble picturing how glacial ice is ever going to have the competency to hold water in at that tremendous potential energy that's got to be there, especially when you realize that this must be a temperate glacier lobe, which means it's riding on a layer of basal meltwater and is riven with moulins and fractures and interstitial cavities. It is not going to be a good material for holding water in at any extreme hydraulic pressure. That's why I'm thinking maybe we should consider that there might be an alternative explanation, which we won't get into today, but maybe in a future talk we could do that. So the last slide will be this one right here. Here's Pardee's calculation for the flow out Clark Fork, 9.46. That's what we just saw with the profile of Atlanta. Victor Baker's calculation down here below the ice dam was 17.1 cubic miles per hour. The flow through Wallula Gap is 10.78. What does this suggest to you? Some discrepancy going on here. Why is Victor Baker's almost twice what Pardee's was? And one assumes that if this was correct, which is based on the Chesney formula, which should be fairly correct, the outflow, 9.64, the flow through Wallula Gap is greater than the outflow from here, and yet the ponding was so great above Wallula Gap that it formed a 1,000-foot deep temporary lake. So think about that.
Could it be the density of the area? The density?
No, I think what it is that we have to consider that there were multiple sources of flood water. Pardon me?
Multiple tributaries.
Multiple tributaries. Right. My thought is that the sole source of water couldn't have been here. And why is this almost double? Well, my first thought is that there are gravel pits along in here that I've looked at that have Purcell Trench provenance in it, which means there are rocks in gravel pits in here that came from the Purcell Trench up here. So I'm thinking that this is probably going to be evidence that this flow was the combined flow of Purcell Trench and Clark Fork coming down this way, and augmented by flows coming separately over this way. And this is why you could have 1,000-foot deep ponding above Wallula Gap right there. There's a lot more I could show you. We didn't even get into looking at the evidence over here in Lake Missoula or the evidence down here, but maybe we can do a future lecture where we could explore all of that. So again, if anybody's interested, talk to Brad over there, because we're going to be organizing another trip out there this summer. And I'd love to have all of you come with. Also, make a donation to the AGS.